Hi, I'm Guo Cheng Guang, secondary one for NS High School. Over here, for this lesson, we're at our organic chemistry with organic chemistry chapter 1, classification of organic compounds. Well, still, although we're saying about organic chemistry, and in organic chemistry we need to know about organic compounds. But for these times, we're just using inorganic compounds. Well, for these inorganic compounds, what we're finding is actually we're using these inorganic compounds just to help us revise or learn. And we're using inorganic compounds in these calculations. Like we can calculate for the first part that we had, which is in electrolysis. For the first part, we could calculate time taken, the mass that we get, or the currents that we need, the charge that we need, and things like that. So that's for the first part there. Then for other parts, you can also find energy. For example, heat energy, or activation energy, bond energy, internal energy, free energy, and in free energy it consists of Gibbs and Helmholtz. Okay, so those are for energies. You can also find for all those that are not energies. For example, heat capacity, specific heat capacity at constant volume, or specific heat capacity at constant pressure. And then enthalpy change, entropy change, chemical potential, and these are examples of what we could find using it. So first part is in electrolysis, which we had electricity like current. And for this part right now, when you look at these examples, they're actually all starting to have heat. But heat, this part, we're not saying about pyrolysis, which is you break down them by heat. There's not that part right now. But this heat, you can calculate for amount of heat that you need, to heat it to a certain temperature, and things like that. Or you can even start enthalpy in this part. So first of all, we need to know for our heat energy what we represent it with. So heat energy, we're using Q for it. But this Q, if we were to write it out, how should we write it out? Is it dQ? For the increment in Q, should we write it as dQ, delta Q, well, capital delta in this part? Or should we write it just as this small delta Q? Which way should we write it as for this part of Q, just to show that increment? So let's take a look at them step by step to see whether they make sense. First part, dQ, small d, okay? So small d, Q, in this part, well, you want to use it for this part, that means you're using it in integration, or you can use it for that. Well, dQ in this part, that means when you want to integrate it, you want to differentiate it, that has become state property. But wait, Q in this part, heat energy. Heat energy is always transferring. So that means Q is a process property. So it seems like that it's not very suitable in this case. Well, how about capital delta Q? Now capital delta Q, you're only saying it is for an increment in Q, just that increase in Q. Well, it didn't say whether state or process. Wait, although this one we may use, but how about let's look at delta Q? Well, small delta Q, not capital delta Q anymore. So small delta Q in this part, well, you could also use it for differentiation. Well, at this part it also says that it is a process property for this part, so you can use it in differentiation and at the same time process. So that means the best part that we'll actually use will be for small delta Q. So this is the most suitable part that we can use. So you can use delta Q over dt, something like that. Okay. So the next part is we have to decide on what kind of questions we're starting with. Wait, we want to know what kind of questions we want to start with. So, C, well, let me just tell you, C in this part, it shows the heat capacity for this part. So what should our C be? So there are two ways that you can use it. It's either delta Q over. So here, when you have heat, like you have something related to heat, then you have things related to temperature. So is it delta Q over delta T, small delta in the numerator, capital delta in the denominator, or should we start with just Q over delta T for this part? So let me just tell you, the case that we're starting with right now is only here. So it's just still constant heat change or heat transfer here, where we still haven't considered about this case here, whereas the heat transfer is not the same. So this a simple case first. So in this part, well wait, that means we can write it as Q being equal to C delta T. Well, you can write it like this, but let's just think of it first. How about like we think about it in life? So like you have one small cup of cold water and you have another large cup of cold water. Then you try to fill them, like which one is more colder. Although they're like at the same temperature, these two glasses of water, of cold water, they're all at the same temperature, but then you fill the cup with the larger cup of cold water it feels like more colder. Well, how does that apply here? It looks like that this heat capacity is the same, but then it doesn't make sense if this is a constant for all of them. So actually, for this heat capacity in this part, let me just tell you, why would you fill those with the larger cup of cold water feels more colder? Actually, this heat capacity here, you still have an M. Then you times, well, I just tried this smaller just to show that these two are different, although they both represent heat capacity, just that this is our heat capacity that we use at first. Here is our specific heat capacity. Well, how is it specific? You realize that we take out this M, so that means you can say that it is over M. So it's like per unit mass. Well, you can say it like that. So then it becomes specific heat capacity. Then you times delta T, or the increase in temperature. So here is the part where you realize, oh, that's why the larger cup of cold water, it will feel colder here. Alright. So now we have settled these things first. Okay. So then we have found out about these. Just to take note again, Q is that heat energy. Well, you don't confuse it with like in the charge. Okay. Just be aware of that in this part. So now we have known about these things. Let me just say them again. Here is your heat energy. Here is your mass. Here is your specific heat capacity. And here is your increase in temperature for that thing. How about let's start to take a look at our example that we have here. Well, it seems like that we have 3 long examples here. The first example, calculate the quantity of heat required to raise the temperature of 2 grams of water 4 degrees Celsius. That means you want to raise the temperature of the water, well, you can say by 4 degrees Celsius, like that. Okay, you can say raise it by 4 degrees Celsius. And look behind. It is given that our specific heat capacity of water is 4.184 joules per gram degrees Celsius. But wait, there you think, you look at that unit. Degrees Celsius, wait, aren't we supposed to use degrees Kelvin? Like, it is our SI unit. Are we supposed to use degrees Kelvin? We follow the SI unit what? But let me just tell you this part. When you change degrees Celsius to degrees Kelvin, well, the difference in temperature are still the same. Just a little bit of change there. Like 0 degrees Kelvin is almost impossible to reach. Well, 0 degrees Celsius, you can reach it. So that's a little bit of difference in this part. So that means degrees Celsius and degrees Kelvin, you can use them interchangeably. But how about degrees Fahrenheit? Well, let me just tell you, degrees Fahrenheit, you can't use it anymore. Like you have the times, or when you convert it in another way, you may have to divide. Then that changes the whole thing. So it changes the difference there. So that means you can't use like degrees Fahrenheit. So the two units that we can use here will be degrees Celsius and degrees Kelvin. Alright, we have this part clear now. So using this part, we need to find quantity of heat. So actually what we're finding is just Q. So you want to raise the temperature, well, you're given the mass of water, 2 grams. So you can just put it inside here, M. Or if you want to be sure that you get a mark for your working, you put this again. So mass, you get 2. Your heat capacity, you look at inside the bracket, you're given that. So this is 4.184. Downstairs you times increase in temperature. So you want to raise by 4 degrees Celsius, that means you increase by 4 degrees Celsius. So in this part, when you're finding it, like this calculations, well, for the calculation, what you may want to use will be a calculator. Well, that's possible for it. Okay, so well, if you want to use mental calculation, yes, you also can choose to use that. But for these types, well, you can just use a calculator for this. But when you're using it, just be careful that you don't input the wrong numbers. So it seems like that here we'll get 33.472. You can just round it off. 33.5, or you can just put this as an approximate sign. Okay, like this. But wait, this is heat energy. What is the unit for energy? Do you know what is it? Let me just tell you. It is joules. J. Joules. That famous person there you may think of. Okay, yep, it is actually named after him. Okay, next part here. Second part. You want to calculate the quantity of heat required to raise temperature of 2 grams of water. Well, you still want this Q here, so Q you already have this part. 2 grams of water, 2. Well, water 4.184 from 21 degrees Celsius to 25 degrees Celsius. 21 and 25. So subtract that, you get 4. Then here you get times 4 again. So well, you can just use the previous answer. So that means it will become about 33.5 joules in this part. Well, if you just want to double check, yes, you can check it again. Alright. So here we already have 2 examples, right? The third example here, it looks almost the same. So we still want the quantity of heat, that is Q. Then this part, to change the temperature of 2 grams of water. And then yes, it is still water. Then change the temperature from 25 degrees Celsius to 21 degrees Celsius. So that's the difference here. Do you still put 4? You cannot put 4 anymore. since here we're saying about increasing temperature, increase just now 21 to 25. Yes, you increased by 4 degrees Celsius. But 25 to 21, you decreased. So when it is in the opposite direction, you have to put a negative. So here there is negative 4. The only difference from these is just that negative. So here's what you get. Wait, so let's take a look at these answers that we get. The first two parts, they're like almost the same. Just that here you given that temperature, here you didn't. So let's see at this part. That means from these first two examples, you need to give that 2 grams of water 33.5 joules of energy. But in the last example, what does negative energy mean? So you get 25 degrees Celsius to 21 degrees Celsius. Then you need to give it negative energy. Well, negative energy is actually taking the energy away from it. So just take the energy away from the thing, it will cool down. Or like it's just lesser heat energy for this part. Okay, so that is actually pretty much what we have in these parts. Well, you have this mass, it is definitely very important here. Okay, because like for a different amount or a different mass of the substance that you are going to have, different masses, you need to give it different amount of energy. So that's the big deal about here. Although sometimes you may write it in this form, just take note, this for a different mass, you need to change it. For a different actual heat capacity, you also need to change it. But here, you just need the heat capacity of the substance times the mass that you're given. So this part then you're done. This part you have to be really aware of that. Okay? So I think for this part we are clear so far. So this is actually the first time that we're starting to have things about heat. Alright, so this lesson I'm just going to end it here. So if you like our videos, don't forget to subscribe to our channel. And see you in the next lesson. Thank you for your watching.